Hello, today we are starting the third section in the first module of Physics HSC. And this is talking about planets and satellites, which are very similar things. Planet circles around a star, satellite will circle around a planet. Um, and they really combine circular motion and projectile motion. So we looked at projectile motion and we said, okay, you have the ground here and a projectile is fired and it shoots up, moves in a parabola, and then hits the ground. If you imagine a projectile which moves so far along the ground that it actually, moves around the curvature of the Earth, so the Earth is this big, then you can conceivably imagine that once it's instead of hitting the ground here, it continues to, move in projectile motion around the Earth down here and back up to here where it began. And this is an oversimplification, but it's essentially how satellites such as the moon stay moving around the Earth. We said in projectile motion that horizontal velocity is constant, and that is true in satellites. The horizontal motion is constant. Just what is considered horizontal changes where you are. So here, a tangent to the Earth at this spot, that is horizontal. But over here, this direction would be horizontal compared to this tangent of the Earth here. So that's how a projectile relates, that's how satellites relate the last two sections that we've done. Now let's look at these equations. Let's look at them for what they are first and then relate them to satellites. So determine the force of gravity between two objects. So any two objects, even these two marking pens, will have the force of gravity pulling them towards each other. That force is going to be equal to capital G. Don't confuse with lowercase g. Capital G is the universal gravitational constant, which is 6.67 times 10 to the negative 11. M and M, capital M, these are the two masses of the two objects. Usually capital M we say is the big mass. So if it's the moon and the earth, we say the earth is big M, the moon is little m. The two pens doesn't matter, right? These pens are about 10 grams each, so 0.01 kilograms. Divided by r squared. R is the distance between the objects. So if I hold these like this, they're about 20 centimeters apart. So that's 0.2 meters. So if you put all those factors together, you get a force of about 2 times 10 to the negative 13 newtons, a very, very, very tiny number, as you'd expect. These are not visibly attracting to each other, right? There's not much force here because their masses are very small. Okay. Um, how this relates to satellites. So satellite, again, if I draw the Earth, I try to draw Australia, there it is, there's Tasmania, and we have a satellite going around it. Here's my satellite. It could be the International Space Station, for example, and it's moving around the Earth in uniform circular motion. The force of it pulling towards the Earth is the force of gravity, is this force here. So if you wanted to calculate this force, you would need capital G, which is a constant in your data sheet, 6.67 times 10 to the negative 11. Big M, which is mass of the Earth, which is also on your data sheet, mass of the satellite, and r squared. Now r, the distance between them, you've got to be really careful. It's not the distance from the surface of one to the surface of the other, it's actually the distance from the center of one to the center of the other. So if you're given the height of the satellite above the Earth, this value, you've got to be really careful to also include the radius of the Earth. The radius of the Earth is in your data sheet. So the radius and the mass of the Earth, both in your data sheet, so is universal gravitational constant. For this equation, if it's to do with the Earth, a lot of information is in your data sheet. You could get questions with very little information in them for you to try and solve. Okay, now this second equation here for little g, this is the gravitational acceleration. This equation is not on your data sheet. It's not here at all. There's no little g equals. So so you're going to have to remember it. Now, this equation is very easily derived using Newton's law of universal gravitation, this equation here, and his other well-known law equation, F equals ma, right? If you substitute, if you use the special case of F equals ma, where you are standing on the planet of the Earth. So if you're standing on Earth, A is going to be equal to 9.8. The force is going to be your weight force, and your mass is your mass. So if you take this special case, where weight is equal to m little g, you rearrange it as like little g, it's supposed to be g, is equal to F divided by m, force divided by mass. I suddenly can't write. There we go. And we, oh wait, no, sorry. Forget I said any of that. You don't need to rearrange it. You substitute this force in here for this force in here. Yep, you get 𝐺𝑀𝑚 over r squared is equal to ma. In that case, little mass will cancel with little mass, and you end up with acceleration is equal to gm over r squared, which is exactly what you get here. Okay, and this equation can be used to solve any problem for this third part of the dot point here, predict the gravitational field strength. So that could, well, either of these two equations. So if they want the force of the gravity or the acceleration due to gravity, you can calculate it quite easily, including at the surface of a planet. So be very careful. If you're calculating something at the surface of the planet, r is going to be equal to the radius of the planet. That's all you have to do. So you can try it for yourself. All of these values for Earth, as in mass of the Earth, radius of the Earth, are all given in your data sheet. Try it out and see if you get a value of about 9.8 meters per second per second. You should be able to get that. I just want to point out one more equation which is not in your data sheet, but is really useful for calculating any kind of orbit. If we go back before to that drawing I had of the Earth, there we go, it's terrible Australia, and a satellite moving around the Earth. Yep, we said it has the force of gravity pulling it down towards the Earth, and that is the force in F equals 𝐺𝑀𝑚 over r squared. Now that force is also the centripetal force, right? It's also Fc, which from a previous video we know is mv squared over r, which is in your data sheet right here. Fc equals mv squared of r. It's even right above the gravitational force. Now, in this example, that force is the same force. Force of gravity is the same as the centripetal force. So we can say that, well, this equation for force of gravity is equal to this equation for the centripetal force. We say that G big M little m, yep, over r squared. Mouse isn't very happy today. Is equal to mv squared over r. Now you can do some really, really cool things with this formula. Remember before when I said you knew a lot of values about the Earth, but you didn't have the mass of the satellite when you're trying to calculate mass of the satellite here? Well, look, mass of the satellite's in centripetal, and it cancels out with mass of satellite in the gravitational force as well. You also have this radius here, which is for centripetal force, is the radius of the circle, and that's the same as the distance between the objects here. So in fact, we cancel out one of these squareds. So you get v squared is equal to gm over r. So you would need to know r. So if you're given the height of the satellite, plus you add the radius of the Earth, mass of the Earth is given, capital G is given, you can calculate the velocity of your satellite. Get rid of that squared there and put a square root over here. You have a formula which converts height above Earth into the velocity of a satellite, which is a really useful thing and is not on your data sheet. So I recommend learning how to combine these two equations in order to get there. And it's also useful to know how to combine these two equations, right? This one and this one, in order to get this one, which is in the syllabus but is not in the data sheet. That's all from me.